Okay, what we're going to do now is learn an alternative method for describing curves. And we're going to call this method parametric curves. We're going to talk about parametric equations. And what I'm going to do is use the circle to begin with, and I'll branch off from there. Now, for example, so let's look at a circle. X squared plus y squared equals 1. Probably from the very earliest time that you were taught that there is an equation that can describe a curve or an equation that could describe a circle, you were shown this. And you begin to recognize, this is the equation of a circle of radius 1. Now, so that was your introduction, this traditional way of writing an equation for a circle. But then you took trigonometry and you learned an alternative way to talk about points on that circle. Now, x squared plus y squared equals 1 is fine. But when you took trig, you were taught this method. You said, okay, if this is the angle theta, x equals cosine theta and y equals sine theta. And this is what you used in trigonometry extensively. Okay. This is a parametric representation of that circle. And that's what you studied in trig. This theta, this is the parameter. And whenever we represent a curve parametrically this way, we need to set the bounds on the parameter. So in this case, for the full circle, I'm going to make theta go between 0 and 2 pi. Now you might wonder, well, why do we even do that? Why not stick with this tried and true method of representing the circle? Well, if you think back in trig, you'll notice there was a lot of advantages to looking at the x coordinate as a function of theta, x equals cosine theta, and the y coordinate being a function of theta, y equals sine theta. There was a lot of advantages in representing the curve that way. Now I want to look at some of that now. And let's think about a circle, x squared plus y squared equals, let's say 4. And the parametric representation of that would be x equals 2 cosine, and let me use t instead of theta. Let me just use that as a standard because we're going to be dealing with other curves other than circles. So I don't want us to, I just want to use a standard of t. We won't always be talking about an angle. So x equals 2 cosine theta and y equals 2 sine theta. This is a parametric representation of a circle of radius 2. Now, I'm going to think about this. What if I have t between 0 and 2 pi, this will of course give us the whole circle. But what happens if we only want to get a quarter of the circle? Well, in that case, I could limit my this parametric set of parametric equations to be between 0 and pi over 2. And that would give me a quarter of the circle. So let's take a look at that real quick. So here we are. We have the circle. X squared plus y squared equals 4, and there it is. Now, notice down here in the second part here, I've got the parametric representation. So let me turn that on, and I've got t going from 0 to pi over 2. So you notice there in blue, it does a quarter of the circle. Now, we could sketch as much of the circle as we wanted by simply changing these boundaries. Let's suppose I want to go from pi over 6 to pi over 2. Then you see that part. Okay. So when we define these, defining this curve with these parametric equations, it makes it much easier to manipulate, to just show part of the graph. That's one of the things we can do with this parametric representation. Now, while I'm at it, let's just look at this. Let's suppose I want to go 0 to pi. Okay, there's that. Now, I don't know if you've ever thought about what would happen if I swap these. This is 2 cosine t. What if down here I put, in place of x, I put 2 sine t. And in place of y, I put 2 cosine t, like that. And and let me still go from 0 to pi. Okay. You notice what happens. Let me turn this one off. Okay. Notice I get a little bit different graph, right? Where this one up here, if I'm going from 0 to pi, it starts here and sketches this way. So let's think about that a little more. We have this set of parametric equations. And I want to just plot some points for this curve, for the curve described by this. The x-coordinate is 2 cosine t, and the y-coordinate is 2 sine t. So we plotted it with our Desmos, but let's see what happens when we just plot a few points, and how would we even do that? Well, let's look at that. So here we go. This is pi here. So what I can do is I can just put in some various values for t. Maybe I'll put in a 0. Let's do pi over 6, and maybe a pi over 2. Just a few values. 3 pi over, well, let's do 2 pi over 3. 2 pi over 3. 2 pi over 3. Let's just plot a few values here. And I get the x, which is 2 cosine t, and the y, which is 2 sine t. Okay, we'll just plot a few values here. Now, if I put in a 0 for t, I get an x-coordinate of 2. And when I put in a 0 for t over here for sine, I get a 0 because the sine of 0 is 0. So we get this point right here. Okay? That's the very first point on our journey around this half circle. Now, if I put in a pi over 6, for the x-coordinate, I get 2 times square root of 3 over 2. And over here, I get 2 times 1/2. Because remember, cosine of pi over 6 is square root of 3 over 2. And the sine of pi over 6 is 1/2. So we get a point, maybe, up here. And then we've got pi over 2. So let's put in values for pi over 2. Well, the cosine of pi over 2 is 0. So the x-coordinate is 0. What about the y-coordinate? Well, it's 1. So we get a 2. So we get this point up here, right? 0, 2. Now I keep going. I was going to plot 2 pi over 3, but you see the idea. You see the way this goes. It plots, the circle plots this way. These half circle plots this way. Now, when we parametricize a curve and we want to show the plot of that curve, if you're asked, well, plot the curve, plot your parametric equations. There's more than just the curve. There it is. There's a curve. There's a direction to it. And you see the way this curve is plotted. Now, what I want to do is I want to look at the other way we parametricize this curve. And what you're going to find is there are lots of different ways we can parametricize a given curve. Some ways are more convenient than others. We parametricize this circle of radius 2 with x equals 2 cosine t and y equals 2 sine t. So that's the way we plotted this one, but we also plotted it another way. We plotted it x equals 2 sine t and y equals 2 cosine t. So let's take a look at that one, the direction that that one's plotted. Okay, so here's the curve, and this is when we set the parameter of t to go from 0 to pi. Let's see what happens. When we put in a 0, this first term here is 0, and cosine t, the y-coordinate, is just going to be 2 times 1, right? So 2. So what we get is, very first thing, we have the graph starting up here. Now remember, when we had the x was 2 cosine t, we started down here. So this is looking a little different. I mean, the curve is the same, but the direction of the plot's different. Now let's try the pi over 6. Well, if we put in the pi over 6, notice we've got 2 times 1/2 right there. And over here is 2 times square root of 3 over 2. So you can see, we get this point down here, and it's clear the graph is moving this way. Now, if we put in a pi over 2, this is going to be 2 times 1. And this over here would be 2 times 0 because cosine of 0 is 0. And sine of, well, I misspoke. The cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So we get this point, 2, 0. So you can see, yeah, the graph is being plotted this way. So we've looked at 2 ways that we could describe this circle of radius 2 parametrically. One way gives us a counterclockwise rotation. That's the way we're used to looking at it from trig. And the other way gives us a clockwise rotation. So we have these 2 ways to parameterize the circle. And let's just see that it works. Now, remember the equation for this circle of radius 2 is x squared plus y squared equals 4. So let's see if this works. If x is 2 cosine t, here's what we've got. We've got 2 cosine t squared. If y is 2 sine t, we've got this 2 sine t squared. See the x and the y. Let's see what that equals. Well, this is 4 cosine squared t plus 4 sine squared t. And let's see what that equals. Well, let's factor out a 4, and we get this. Cosine squared t plus sine squared t. And this equals 1, so this just equals 4. So, yeah, x squared plus y squared does equal 4. And we could show that for the other one too. We could show it for this one too. But those are not the only 2 ways that we could parameterize a circle. Remember, the circle of radius 2 is equal to this. I mean, that's the way we're used to looking at it. What if I solve for y? Well, if I solve for y, I get 4 minus x squared. The square y equals 4 minus x squared. Now, that's the top part of the circle. What if I do this? And this is one quick way that you can parameterize a curve where you have y equals something in terms of x. You can just say, well, I'm going to let x be t, and I'll let y be the square root of 4 minus t squared. There. And you have, that's a set of parametric equations. That's a quick way to find a parametric representation. I just said x equals t and y equals 4 minus t squared, which is just this. Now, you might say, well, does that really work? Well, I mean, it's pretty obvious it works, right? Because all we did was substitute in a t for x. But let's try this. Let's try the x squared plus y squared, and that should equal 1. Let's see what it equals. We've got t squared, that's the x, plus the square root, whoops, let me write that better, the square root of 4 minus t squared, squared. And let's see what that equals. Well, this is t squared plus 4 minus t squared, and that equals 4. So yeah, x squared plus y squared does equal 4, and that's what should have happened. That should have equaled 4. So you can see, yeah, this parameterization works also. But anyway, so if we're wanting to parametricize a circle, just in general, let's suppose we have a circle. Let's suppose we have x squared plus y squared equals 25. And we want to come up with a way to find a set of parametric equations for that circle. Well, you can just say x is the radius times the cosine of t, and y is the radius times the sine of t. And then you can, t, if you want the whole circle, it'd be like this. This is the way we can find a parametric representation for a circle, just a basic circle like that. X squared plus y squared equals 25. But what if you have something that's not a circle? Let's suppose we have an ellipse. Let's suppose we have x squared over 9 plus y squared over 25 equals 1. And we would like a set of parametric equations for that thing. So how would we find that? Well, let's try this. Let's let x equal 3 cosine t and y equals 5 sine t. And let's see if that works. In other words, I want to find out if I put this value in for x and this value in for y, will this left side equal 1? If it will, then I found a way to parametricize this curve. So let's try it out. In for x, let's put in a 3 cosine t. And you can see why I chose 3, square root of 9, right? So when I square 3, it's going to cancel out with the 9 on the bottom. Okay, let's look at this one. We've got 5 sine t over 25 equals 1. And let's see here, this is 9 over 9 cosine squared t plus 25 over 25 sine squared t. Let's see if that equals 1. Well, this and this cancel. So yeah, cosine squared t plus sine squared t. Yeah, that does indeed equal 1. So if we want to parametricize an ellipse, let's suppose we've got x squared over a squared plus y squared over b squared. Well, just let x equal a cosine t and y equals a sine t, and that'll do it. So we want to be able to really quickly find a parametric representation for some of these curves. So anyway, this is just an introduction using, circles and ellipses, very basic circles and ellipses. They've not been shifted. They're centered at 0, 0, centered at the origin. So we'll branch out and we'll look at some other curves and a way to find a parametric representation for those.